We have two formulas for calculating angular momentum. When should we use them? We have the r cross p angular momentum, and we have the I omega angular momentum. The L equals mRV is just a special case of the r cross p angular momentum when r and p are perpendicular to each other, like in uniform circular motion. For point particles, you can use either formula to calculate its angular momentum. However, if you have a rotating rigid body, then you must use the I omega version. So either one for point particles, I omega for rigid bodies. If you have a rigid body, you must use I omega. If you have a point particle, you may use either one. A point particle is nothing more than a rigid body that consists of just one particle. As you may recall, this I omega angular momentum was derived from the r cross p angular momentum. We treated the rigid body as a collection of point particles and calculated r cross p for each of those point particles and added them up together. When we added them up together, we got I omega. In particular, then, a rigid body of just one point particle, we just have to calculate r cross p once, and we'll end up with I omega for just one particle. So that's the intuitive reason behind it. A point particle is a rigid body that consists of just one particle. Mathematically, you can see as follows. We have L as r cross p. We know p is just mv. Then we can pull the m out of the cross product and then multiply and divide by r squared. Mr squared is just the moment of inertia for a point particle, and r cross v over r squared is omega for a point particle. And so we see that the two are equivalent in the point particle case, even mathematically. It is also important to note, though, that for a rigid body, the angular momentum can be broken into a spin and an orbital component. And these components are going to correspond to both the r cross p and the I omega. So the way you can do it is, imagine we have a rigid body rotating about its center of mass, but at the same time, the center of mass is moving about another point. In that case, we have our rigid object is spinning. It is spinning about its center of mass, but at the same time, the center of mass is orbiting around another point. If this looks familiar to you, it should, because this is the scenario for the Earth. The Earth orbits around the sun, and as it orbits around the sun, it is also spinning on its axis. It is rotating about its axis and moving about the sun. So we can see that angular momentum can be broken into this spinning component and also this orbiting component if we think about the rigid body's center of mass. The rigid body spins about its center of mass, while its center of mass orbits around another point. Consistent with the fact that you can use either r cross p or I omega to calculate angular momentum for a point particle, a point particle can be viewed as either spinning or orbiting. This is because a point particle has no structure to it. It can't spin. All it can do is move about another point, and that motion about another point can either be interpreted as the point particle spinning about that point or orbiting. And so you see here, for example, here's a point particle and it is moving about this point in the center. Is the point particle orbiting that point, or is the point particle spinning around that point? Really just depends how you look at it. It could be viewed both ways. Getting back to the math, you can write the total angular momentum of an object, and especially thinking about rigid bodies here, as follows. We have the angular momentum of our rigid body about its center of mass, plus the angular momentum of our rigid body's center of mass about another point. We call this the spin angular momentum and the orbital angular momentum, where the spin angular momentum is this I omega term, and the orbital angular momentum is the r cross p term. You may see this formula for total angular momentum sometimes, and this is where it comes from. It's just decomposing the total angular momentum into orbital and spin components. We therefore see then that a point particle can be viewed again as having either spin angular momentum or orbital angular momentum. In broad strokes, I omega is spin angular momentum and r cross p is orbital angular momentum. Nevertheless, the rules still follow that we spoke of before. For point particles, you can use either I omega or r cross p to calculate its angular momentum. And for rigid bodies, you can use I omega to calculate its angular momentum, but you cannot use r cross p. If the rigid body is both spinning and orbiting, it will be easier to break up its motion into both spin and orbital angular momentum components in order to calculate it. And in that case, you're applying r cross p to its center of mass, which conceptually is reducing the rigid body to a point particle anyway, and the I omega is being used for the angular momentum of the rigid body about its center of mass.